Hello, my name is Gary Finley. I'm an electrical engineer with 25 years experience, and I'm going to show you my PCB design methodology that has worked quite well for me over the years. The most important document in any project is the bill of materials. In it, I track pretty much everything about the entire design, starting with each of the large components that immediately go into the bill of materials on day one. I create a component tracking section of the bill of materials that allows me in the end to just put a number in for a specific version of the board I want to build, and it will show me any deficiencies that I have. If you have a full accounting department and a purchasing agent, you won't need that. In a small company environment, that's very useful. Also in the bill of materials, I track whether or not the schematic symbols have been created and have they been checked, the layout geometries, all of the different infrastructure elements, and whether or not the part belongs in that infrastructure diagram, and I positively mark it in the bill of materials that it's gone into the diagram. If it's not in the diagram, and it should be, then obviously you've made a mistake, and it's easy to leave something out of, say, a reset diagram. So this is the way I track whether or not all the parts have made it into the various elements of the infrastructure. And then, of course, we track costs both in terms of unit price and in terms of higher production quantities. Then we go to the full mechanical concept, and what you see here is my solution to putting a circuit board in a CPU LGA clamshell socket, and that ended up defining the perimeter of the board. Now we know exactly how big our board's going to be, so we have a concept of how many of the large components and the various functions we can put on it, and each little icon represents a different kind of architecture, a different emphasis on memory or FPGA or the number of components. And from this, I was able to present this to the team, and they were able to easily pick out which elements they wanted, and they chose among the best options. From that, of course, we go straight to the block diagram. As every big component goes into the block diagram, it goes into the bill of materials as well, and the schematic symbol and layouts footprint start to get created along with the block diagram and all the other diagrams that I'll show you coming up. Once we know what all the major parts are going to be, we can go to a detailed mechanical diagram to make sure that everything really is going to fit. And this, of course, has many layers that I've turned all on, and you can see that all the different stuff, all the way down to drill holes, heat sinks, and all the other elements of the mechanical solution are shown in this diagram. Now we start working on the most congested part of the routing. You need to find out if the routing is going to work, and the way to do that is you pick the most congested part of the routing and attempt to actually route it. In order to do that, you have to have the stack up, because you need to know the number of signal layers you have to work with. The stack up is determined by the allowable board thickness, how many traces you want to get between your vias. I always go signal plane, stack up, and I get the number of routing layers out of it. Then I pick the most congested area, I rotate the chips around, and each one of these colored arrows represents a different signal layer in the stack up. So obviously if I have more colored arrows, more different colors than the number of layers that I have available in my stack up, then I've got to do something else. I've got to rotate it some more, reduce something in the design, or it simply isn't going to work. Then once I think I have a theory that's going to work, I prove the theory by actually creating what we call the bubble diagram, where every single pad on the components that are involved in the congested area actually show up here. The powers, the grounds, all the signals are color-coded, and I print a whole bunch of these out, one for each signal routing layer that's available, and I start routing all the traces. And if I get to a point where I run out of routing layers, I throw it away and I start again, or I reduce something or add something, and by the time I'm done with this, I know that my most congested routing can be done. This is a very, very important part of the design. You breathe a sigh of relief when this stage is done. Then we go to infrastructure. This, forgive me for some of the blurred out text here. Some of this is semi-confidential, but basically there's the reset diagram. You make sure all the voltage standards and signal polarities are correct. This is a good diagram for that. Very similar with the clock. You make sure that the voltage standards and the IOs all match up, and also all the FPGAs need to have a clock on every single side. This is a very good diagram to show where all the clocks are going. The I2C bus is used to monitor the temperatures, the voltages, and the currents, as well as trim the regulators. And also there's some local memory on board. We can store serial numbers and other things about the board. And my I2C buses tend to get fairly complicated because it's a lot of good infrastructure that people like to use to test the boards. The JTAG infrastructure is very important as well. It's used to both troubleshoot FPGAs as well as test the board in production, and you need lots of various switches to switch out different legs of the JTAG bus for the different purposes. At this point, we go ahead and actually build the CPLD. We'll put all the functionality into it, make sure that it actually fits so that we don't have any surprises. This is the glue CPLD I'm talking about. It has to work when the board comes up, so we can't afford to have any surprises. So we build the CPLD at this point. Then now we know the bill of materials is really fleshed out except for the power structure, but now we know from all the other infrastructure what power is needed. And I go through all this process of determining what different voltage rails we have and how they need to be segmented if they need to be power sequenced independently. I put down all the requirements for power sequencing, and whether or not there's any diagrams, every note I can find I put it in, and then I actually go back, and with the red arrows I show which power has to come up before what, and I make sure that that gets enforced using control signals, capacitor delays, whatever might work in this environment. I then move on to simulating all the regulators that I've put in my block diagram. I have a lot of very good experience using LinearTech Switcher CAD, and I know I can get this down to within 10% performance, both in terms of a 50% step load function and the maximum DC expected current. So, and I understand how to put the parts in, what parameters actually matter for each individual part that's on this diagram. As I do the different LinearTech Switcher CAD simulations, I track how each design test performs. And from this particular spreadsheet, I can pick out the one I like best and then actually use that on the schematic. And there we have it in the schematic. The schematic is now well underway, and we start putting in all the power supply regulator components. And one of the first things we will route in the schematic is actually the congested area. We'll go straight at that and actually begin the layout on the congested area before the rest of the schematic is done to make sure that it actually can be routed the way it was done in the bubble diagram. If any surprises should occur at that point, it's very important to know that. Also, there's a lot of balanced traces these days with all the different high-speed buses, differential pairs, and I keep track of that. It can be done in the layout tool. I double check it in a spreadsheet as well to make sure that the layout personnel got it right in the layout. Now what we see is the I2C bus. This is an ASCII window. What you see up here is a lot of good information. The VHDL developers, everybody loves this window. We put out the total power for the board, basically the temperatures on the FPGAs. We keep track of whether or not they stayed within their expected parameters. All the different regulators. I have the ability to margin some of them here, not all of them, and then measure current on even fewer of them, just the big switchers we measure current on. We have the ability to dump this out to a file. And people like this window. You could go wild with this and create a very nice GUI out of it, but there's a lot of information packed on a small screen there. After all the interfaces, now the board has come back, and we've tested the interfaces, and we can now use our I2C bus to do voltage margining, -5%, +5%, and let the temperature go up to the expected maximum performing temperature, and we keep track of the test and whether or not it passed, and we do this for all the various interfaces that we have on the design until they're all working. Once they're all working, we can go into production. I wrote this particular manual, and it was about a 70-page manual with circles and arrows, blue boxes on almost every single page. And I sat down with a production engineer, and we recorded everything, and in real time I changed the document. Everything you'd expect from something that has to operate remotely on a production floor. And that pretty much concludes my presentation, and this procedure has worked very, very well for me over the last 15 years. I'm sure it will work well for you as well. Thank you for your time.